Before a machine learning model sees a dataset, we get one quiet chance to look at it ourselves. These dots are records. At first, they are just a cloud, many values, many directions, and not much meaning yet. Descriptive statistics are the first map. They tell us where the data lives, how far it spreads, which values are unusual, and which columns move together. That map matters because a model will still fit numbers that are scaled badly, distorted by outliers, or hiding a strange relationship. The goal is not to replace the model. The goal is to stop being blind before we fit one. Center sounds like one idea, but data has several centers. The mean is the balance point. If every value had weight, the mean is where the number line would rest. Mathematically, the mean adds all values and divides by how many values there are. X bar equals 1 over n times the sum of all xi. The median is different. Sort the values, then walk to the middle. Half the data is on one side, half on the other. And the mode asks a simpler question: what value shows up most often? Same dataset, 3 useful summaries. Each answers a different question: balance, position, or repetition. Now add one extreme value. The mean moves toward it because the mean uses every distance. A single faraway point can pull the balance point. The median barely moves. It cares about order more than distance. This is why the median is often called robust. It does not ignore extreme values, but it is less controlled by their size. That does not mean the outlier is wrong. It means the outlier is important enough to inspect before training. In machine learning, an outlier might be an error, a rare but real case, or exactly the kind of event the model must learn to handle. Center alone is not enough. 2 datasets can share the same mean and feel completely different. Spread measures the room around the center. Each value has a deviation from the mean, xi minus mu. If we only averaged deviations, positive and negative distances would cancel. So variance squares the deviations first. Variance is the average squared distance from the mean. Sigma squared equals 1 over n times the sum of xi minus mu squared. Then standard deviation takes the square root and brings the result back into the original units. It answers a practical question: how much movement is normal here? Percentiles add context. A value is not just large or small by itself, it is large or small compared with the rest of the data. The 90th percentile means about 90% of the values are at or below this point. The median is the 50th percentile. Quartiles split the data into 4 ranked regions. That is why percentiles are useful for thresholds, anomaly checks, and reports. They turn magnitude into position. For a model pipeline, a percentile can say this value is not just high, it is high relative to the training data. Machine learning models often see features as geometry. If one column is measured in thousands of dollars and another is counted from 1 to 6, the larger scale can dominate the distance. The z-score transform uses the mean and standard deviation. Subtract the mean, divide by the standard deviation. Z equals x minus mu over sigma. After that transformation, 0 means average, positive means above average, negative means below average, and 1 unit means 1 standard deviation. Now both features speak a more comparable language. Scaling does not magically improve every model, but for distance-based methods, gradients, and many neural network workflows, it can make the geometry much healthier. Some statistics describe one column, others describe pairs. Covariance asks whether 2 variables move together. Up together gives positive covariance. One up while the other goes down gives negative covariance. The formula multiplies paired deviations: xi minus mu x times yi minus mu y. If the products are mostly positive, the variables tend to move in the same direction. If they are mostly negative, they tend to move in opposite directions. But covariance still depends on the original units. Correlation divides by both standard deviations, so the relationship is standardized between -1 and 1. That makes relationships easier to compare across different feature pairs. Let us slow down and compute one small dataset. The values are 2, 4, 4, 4, 5, 5, 7, and 9. Add them, the total is 40. Divide by 8 values and the mean is 5. Now look at the deviations from 5. 2 is 3 below. 9 is 4 above. Values equal to 5 have 0 deviation. Variance squares those deviations, then averages them. For this dataset, the squared deviations add to 32, divide by 8, and the variance is 4. The standard deviation is the square root of 4, so it is 2. That means a typical distance from the mean is about 2 units. Not every value is exactly 2 units away, but 2 is the scale of ordinary movement in this dataset. This is the moment where the formula becomes a measurement. Now step back from formulas and look at shape. These three distributions can have similar centers, but they do not tell the same story. One is compact, most values cluster near the middle. One is wider, values are more spread out. One has a tail, a few values stretch in one direction. Histograms make that shape visible. The interquartile range, or IQR, is Q3 minus Q1. It measures the width of the middle half of the data. That makes it useful when tails or outliers would make the full range misleading. For ML, shape can suggest transformations. A long tail might call for a log transform. A compact distribution might already be well behaved. A strange shape might reveal mixed groups hiding in one column. Finally, let us compute the idea behind correlation with 4 paired points. The x values are 1, 2, 3, and 4. The y values are 2, 3, 5, and 6. The average x is 2.5. The average y is 4. For each pair, subtract the x mean and the y mean, then multiply the two deviations. When both values are below their means, the product is positive. When both values are above their means, the product is also positive. Here the products mostly reinforce each other, so covariance is positive. Correlation then divides covariance by the standard deviations of x and y. The result is close to 1, which matches the scatter plot. The points rise together in a nearly straight pattern. Correlation is not causation. It is a standardized description of co-movement. Before fitting a model, descriptive statistics become a checklist. Where is the center? How wide is the spread? Which values sit in the tails? Which features move together? Are the scales fair? These checks can reveal outliers, scaling problems, redundant inputs, and suspicious relationships. They can also shape decisions, whether to transform a feature, cap an impossible value, standardize columns, or investigate a data collection issue. Descriptive statistics do not make the model smart. They make the modeling process less blind, and this sets up the next layer. Once we understand center, spread, rank, and relationships, the next question is uncertainty. How likely is a value? How surprising is an event? And how should a model reason when outcomes are not certain? That is where we go next. Probability basics. Every ML learner must know. Thanks for watching. Subscribe for the next chapter. Stay curious. Keep following the data before the model.